So today we're going to talk about conservation of mass and momentum. We introduced quickly Reynolds transfer theorem or Reynolds transport theorem in our last lecture. So before we get into conservation of mass, let's review what that was. So we said that Reynolds transport theorem was an analysis or a system. System is not a good word to use. A tool that we can use that converts a system analysis, which is what we defined as Lagrangian, and it's going to bring that to a control volume analysis, which is Eulerian. And the control volume analysis is a lot of times more advantageous for fluid mechanics because we don't really care about the individual particle motion and the interaction of particles. We don't have to keep track of all of the particles in our system. We just need to care about a bulk analysis of some fixed region in space called our control volume, and then information about the mass of fluid leaving and entering our control volume. So a system is considered a closed system. It's a fixed collection of matter, and has a fixed mass. So that's what we call a closed system. The control volume is an open system because even though it's a fixed region in space, material and mass is allowed to flow in and out of it. So that's an open system. It can also deform in time and move in space. So a control volume is surrounded by what we call a control surface. This defines the boundaries of a control volume. And it usually consists of walls through which the fluid can flow or pass, and also represents some sort of physical boundary, such as the wall of a pipe. Or in this example right here, we would have our control volume being, I guess, following the geometry of this canister. And to compare the control volume to the system would include all of the atoms of gas that are located in that spray canister. And even after the spray is released and some of the atoms escape, the system now is, the boundary of the system changes to include all of that escaped gas, whereas the control volume stays constant. So we don't care what happens once the gas leaves. We just need to know information about it as it's leaving. We also defined two different types of properties which were extensive and intensive. So extensive properties, we said, were related to the total mass of the system. And we called this, we used the value of capital B to represent our extensive properties. So examples for extensive properties was our mass, which is M, our momentum. What is the relationship for momentum if we think back to our dynamics course? If we call momentum our variable P, P is equal to what? Yeah, mass times velocity. And because velocity has a direction, our momentum is also going to have a direction. So it's also a vector quantity. And then lastly, energy. Our extensive energy we call E. So next we have what we defined as our intensive properties. So this is what's used in our control volume analysis and our control surface analysis. And it's integrated over some volume or some surface to figure out our total extensive property. So these are just our extensive properties divided by the mass, or if we had it in differential forms, dB divided by dm. So our unit mass would just be our mass divided by our mass, so it's unitless. Our momentum would be mass times velocity divided by mass. And our specific energy would be capital E divided by mass. So in each of these cases, depending on the type of analysis we're doing, these would be equal to beta, and then these would be equal to our capital B from our Reynolds transport theorem equations. So we then derived Reynolds transport theorem. So let's revisit what these mean with a slightly different diagram so we can have a different perspective on it. So Reynolds transport theorem relates the time rate of change of any extensive property B of a system of fluid of particles, defined from a Lagrangian description. That is, by following the system. And it relates this to the changes of B, that extensive property, defined from an Eulerian description. That is, by finding the changes relative to a control volume. So if this is the change of our system, this is equal to a local change, which is the time rate of change of the intensive property beta within the control volume, integrated over the whole control volume, plus the convective change, which is represents the net flow of the intensive properties through the control surface. So convective change, we could think of change due to a changing position. So the diagram below shows at some time t, we have our system. And the system is the blue area with our particles drawn in there, and our control volume is highlighted in red. After some amount of time, our system has moved out a little bit at the right-hand side, and some new mass would be moving in at the left-hand side. And we can relate, if delta t becomes very, very small, we can relate these masses of system moving in and out to what's in the control volume, and we would end up with our Reynolds transport equation. So this is the equation that we will use anytime we want to do some fundamental Lagrangian equation of motion, whether that be conservation of mass, conservation of energy, and conservation of momentum. We will be using this equation. So yeah, in this case, I'm not sure how to write the V with a bar through it. This is volume, and this is velocity. So a bold V is our velocity vector. Bold is a vector. And our fancy V, or our script V, we'll call it, is our volume. So that's basically where we got up to. And we were just about to start talking about a moving control volume. So you'll notice, different from last week, is that the velocity has this subscript here, F/CS. Our control volume doesn't necessarily have to be fixed in space. It can be moving with some object of concern, or moving in a way that makes Reynolds transport theorem a viable analysis. So let's consider the example we have right here. So from a fixed observer, so if we're standing still, and we have the flow of water at A appearing to have a velocity Vf at time t. So that is the velocity of the fluid. And we're fixed, and the blade at B is moving into the stream. So it's moving towards the nozzle. So however, when the blade advances, then at t plus delta t, the flow will change its direction, and then the velocity will become v prime. So for the same point in space, I'll draw this in red to make it a bit bigger. The same point in space, here and here, the velocity has changed direction. So if the velocity is changing direction at some point in space within our control volume, that means we have unsteady flow. So what we can do is we can select a control volume that contains an amount of fluid on the blade, and then move this control volume with the blade. So the velocity of our control volume is equal to the velocity of our blade. So this should be velocity control volume is equal to the velocity of the blade. So then if we did this, we can draw a control volume for the boundary of the fluid, and that control volume is going to be moving at the exact same velocity as our blade. Now, if we select a control volume here, and we move the control volume with the blade, we have this relationship, and we now have steady flow. So at any point within that control volume, with respect to the moving control volume, the velocity is not changing with respect to time, so it is steady flow. The velocity is now only changing with respect to space. So we can always write our Reynolds transport theorem where the velocity is the velocity of the fluid is written with respect to the velocity of that control surface. So if our control volume and our control surfaces are not moving, then this term just becomes 0, and it's just the velocity of our fluid. But if we always write it this way and we understand that this is what this means, then we can never go wrong. So we did talk about quickly the conservation of mass. And the conservation of mass was when we set our beta term. We said beta is equal to mass over mass, which is equal to 1. So if we rewrite our Reynolds equation, our Reynolds transport theorem, then we see that beta term is just 1. And conservation of mass states that any region of matter, so a system, because a system is defined as a fixed amount of matter, it can't be created or destroyed except for a nuclear process. So if we ignore our nuclear processes, then the change of mass of our system is going to be 0. So the left-hand side of our equation becomes 0. And all we're left with is the local mass change within the control volume and the convective mass change due to mass entering and exiting the control volume through the control surface. And we call this the continuity equation. So it states that the local rate of change of mass within a control volume plus the net convective rate at which the mass enters and exits the open control surfaces must equal 0. So let's look at some special cases where we have may have conservation of mass concerns. So the first case is where we have steady flow. If we can I still see the above equation? Good. So if we have steady flow, and we just look at this last term here, the integral, so the convective mass change. The convective mass change is the change of mass due to mass entering and exiting the system. So if we have steady flow, that means it's not changing with respect to time. And we have this integral would be equal to the sum of our mass flow rates out minus the sum of our mass flow rates in. So if this is our system, we have m dot in over here. We have a velocity going out, so we have m dot out over here, and we have m dot out over here. So now let's look at, we have steady and uniform flow. If we have steady and uniform flow, that means our velocity is constant over that area. So instead of writing the integral, we can just take our velocity and multiply it by the entire area. And this would also be equal to our mass flow rate out minus sum of our mass flow rates in. And then lastly, if we have incompressible, steady, and uniform flow, that means the density of our fluid at all of the inlets and outlets, plus throughout our control volume, will be constant. So if the density is constant, then we can rewrite our mass flow rates as our volume flow rates times our density. So m dot equals rho q dot. And if we do that, we can divide both sides by rho, and all we're left with is sum of our volume flow rates out minus our volume flow rates in. I shouldn't put a dot above q because it's already a rate term. So if we have these special cases, we can simplify the control surface term by just considering the mass flow rates in and out. and the volume flow rates in and out of our system, or of our control volume. Let's just review quickly what are our flow rates. So our volume flow rate is the volumetric flow or discharge Q through a planar area, and it's determined by finding the velocity of flow perpendicular to the area. So if our velocity profile is known and integrated, the average velocity can just be given by V, and then we can have Q is just equal to VA. If we have a velocity profile that's not constant, then we have to integrate, and we can integrate using this equation here, where this would be V as a function of R and theta if it's a round pipe. Mass flow rate is simply the density times our volume flow rate. So if we take the same integral and we multiply by our density, if we assume our density is not constant, then we can leave it in the integral. If our density is constant, then it comes out of the integral, and our mass flow rate is calculated using this equation here. So let's do a few examples where we consider conservation of mass. So in this example, we have a tank. It's given that it has a volume of 1.5 meters cubed and is being filled with air, which is pumped into it at a rate of 8 meters per second. So that's the velocity of the air being pumped into the tank through a hose having a diameter of 10 millimeters. As the air enters the tank, its temperature is 30 degrees C and its absolute pressure is 500 kPa. Determine the rate at which the density of the air within the tank is changing at this instant. So what is the rate of change of the density of the air at this instant? So let's start by just writing our continuity equation, which is our Reynolds transport theorem for conservation of mass. That's called our continuity equation. So if we recall, we have the time derivative of the integral over our control volume of our density times dV. So this is our volume. This is how I'll draw volume here. Plus the integral over our control surface, rho, times velocity of our fluid with respect to our control surface, dot product with our area is equal to 0. This is not volume, this is velocity. Just remember, this is volume. Velocity of fluid with respect to the control surface. So before we go any further here, let's draw a diagram to see what's actually happening. So here is our tank. And we have velocity of air entering the tank. We have our normal direction from the area is pointing outwards. Normal to our control surface is always pointing outwards from our control volume. And if we use our conservation of mass equation, we can rewrite the Reynolds transport theorem if we consider our control volume as following the shape of our container. So we have mass flow into our container. Do we have any mass flow out? No, we have no mass flow out. What about our control volume term? Is the amount of mass inside of our control volume changing, or is it constant with respect to time? Right, mass is changing. So if mass is changing and volume is staying constant, now if we just look at this first term, we have mass changing, volume constant. So one thing we have to do anything with this first integral is we have to assume that the density within the tank, assume there's sufficient mixing as air is added, that the density throughout the tank is the same. The density might be changing with respect to time, but the density at the front of the tank isn't different than the density at the back of the tank. So that's an assumption we need to make. The density within the entire control volume is the same. And then if we do that, we can just, since density is not a function of our position within that volume, we can take that first term and we can write this as d rho dt times our volume. So the rate of change of our density times our volume. And then our other term would be the mass flow rate out minus the mass flow rate in. And this is what type of flow? What case do we have here? Yeah, we have steady flow. And arguably this would be considered uniform as well because we have a constant velocity profile. So we could also say this is steady and uniform. In both cases, it would be the mass flow rate out minus the mass flow rate in. So we have no mass flow rate going out. So we have a negative mass flow rate in. And this is equal to 0. And our mass flow rate in term, we can write as rho A times the velocity at A times the area at A. So we can finally write this equation, d rho dt times our volume minus rho A VA AA is equal to 0. So this is our first equation. So one thing that I used to get confused with all the time is how do we know which mass flow rate is negative and which one's positive? Out being positive and in being negative seems counterintuitive. Why wouldn't in be positive? Because it's mass going in, you're adding is positive. So think of it this way. In the Reynolds transport theorem equation, we have our velocity dot product with our area. The direction of the area normal is always pointing outwards. So if our velocity is pointing outward, the dot product of an outward velocity with an outward normal would be positive. So out is positive. If we have velocity going into our control surface, now we have velocity in the opposite direction of our area normal. So that dot product would give us a negative value. So a velocity going into an area normal that's pointing out, we would have positive and negative. So the dot product is negative. So mass flowing out of our system is positive. Mass flowing into our system is negative. And the area normal out is by convention. That is mathematically how we would define the area normal over a control surface that encloses some volume. So we have one equation. we have the rate of change of our density times our volume, which is known, is equal to our density of our gas times the velocity times the area of the gas entering our control volume. So we need another equation. So what's another equation we can use? Flow rate, volume, flow rate, not quite. Is this gas compressible? Yeah, so we have a gas being forced into a container. We're adding more mass. So we're adding more mass. That means we're changing the density. We're changing the pressure. And the relationship between pressure and density. And if we know the temperature, which is given to us up above at some point in time, so we have temperature is 30 degrees C and pressure is 500 kPa. That's enough information now we can use the ideal gas law. And we can solve for the density of that gas at that time that we were trying to find the rate of change of our density. So we need to find PA. So find using ideal gas law. So our ideal gas law says that pressure A is equal to our density times our gas constant times the temperature of A. Well, we can rewrite this as density of A is equal to pressure at A divided by RT. We know the pressure was 500 kPa. So 500 times 10 to the 3 PA. Our gas constant for air, if we look in the appendix, is 286.9 joules per kilogram Kelvin. And our temperature, which is given to us, is 30 degrees Celsius. We need to write this in Kelvin. So 30 plus 273.15. And that would be Kelvin. So if we plug those numbers in, we should get our density is 5.752 kilograms per meter cubed. So now let's substitute back into 1. So we have the rate of change of our density times our volume, which is given to us in the question as 1.5 meters cubed, minus our density now, 5.757 kilograms per meter cubed, times our velocity. Our velocity was 8 meters per second. In the area, it said that the diameter of the hose was 10 millimeters. So we have pi times our radius, which is 0.05 meters. Sorry, 0.005, it's only 5 millimeters squared, and that'll be units of meters squared. This is all equal to 0. So when we rewrote our equation, the question is, why isn't our velocity minus 8 meters per second? When we wrote our form of our continuity equation in this form here, we already considered the direction, whether the velocity was positive or negative with respect to the control surface, whether it was going in or out. And that's with this positive negative sign. So because we already have the negative sign here, We don't need it later on. All we care about is the magnitude of the velocity now. So this term here is positive 8 meters per second because we already have the negative sign out front. We've already accounted for it. So if we solve this, the only thing we have left is the time rate of change of our density. And if we solve this, we should get 2.41 times 10 to the minus 3 kilograms per meters cubed per second. So in this case, the question in the chat is just, can you draw the control surface? So the control volume, the control surface outlines the control volume. So the control volume is this entire space. So really, how I should draw this is this is our control surface. And the entire space is our control volume. Now, the only area where a mass is flowing through our control surface is right here at the inlet. So we only need to consider the integral over where mass is actually entering. Everywhere else of our control surface, there's no mass entering or exiting. So we only care about that one little inlet. But our control surface is in the red, and that defines the boundaries of our control volume. So that's for a fixed CV. CV is not changing with respect, it's not growing, it's not moving, but the amount of mass inside of a control volume is changing because it's a compressible gas. So now let's look at an example where we have a moving CV. So in this example, we have a rocket sled, and it's propelled by a jet engine that burns fuel that enters the engine at C at a rate of 60 kilograms per second. The air duct at A has an opening of 0.2 meters squared and takes in air having a density of 1.2 kilograms per meter cubed. If the engine exhausts the gas relative to the nozzle at B with a velocity of 300 meters per second, determine the density of the exhaust. The sled is moving forward at a constant rate of 80 meters per second, and the nozzle has a cross-sectional area of 0.35 meters per second. So in this, the diagram already has the control volume drawn for us, and is outlined in red, which is, I guess, the control surface. So what is going on in this problem? What are some things we need to consider? Is this compressible or incompressible, do we think? Yeah, it's compressible, or it's likely compressible. We have an air-fuel mixture. We have information about the density, and it's asking to find the density of the exhaust. So if it's asking us to find the density, and we know the densities of the contents that are mixing, it's probably a compressible system. Also, because it's traveling so quickly, this might also be an indicator that it could be a compressible situation. We have combustion. Generally, those are compressible situations. So we have a compressible air-fuel system. And so the density now we need to consider is different at the inlet A and the exhaust at B. The other thing we have to assume is because it gives us our mass flow rates, kilograms per second, and our velocity exiting, we're going to assume that we have average velocities. So we're assuming that the velocity profile exiting at B and entering at A is more or less constant. So we're going to assume it's compressible, and our velocity, or we'll use average velocities. So next thing, is our control volume steady? Yeah, our control volume is moving, but is the flow in our control volume steady? Is it steady flow? So is the flow within the control volume changing with respect to time? Right, so if our control volume moves with the rocket, then the flow is steady, and there's no local time rate of change of the air fuel mass within the control volume. So the rocket is not accumulating mass, and it's not getting lighter as it travels, and we're assuming that the flow is steady and there's no net change within the control volume. So we'll say flow is steady in the control volume. So the first thing we can do is we can figure out what is the velocity of the gases with respect to our control surface. So the velocity of A with respect to our control surface, we define as equal to the velocity of the the velocity of A minus the velocity of the control surface. So what is the velocity of A with respect to the control surface? What is the absolute velocity of A? So I got the velocity of the control surface, 80 meters per second, no relative velocity. So the velocity of A, if we consider we're moving on the control surface, would be 0. This is moving through still air. So the absolute velocity of A is just 0. It's not moving. So the rocket is what's moving, and the velocity of the air itself that would be entering at point A is just sitting still, and the rocket is rushing through it, and that's what's causing the relative velocity of VA. So then all we have left is the velocity of our control surface. Let me get rid of this slash so it's not confusing. And the velocity of our control surface is equal to 80 meters per second. So then the velocity of A with respect, the velocity of the fluid flow at A with respect to our control surface then is negative 80 meters per second. Now we're back. So if we were sitting on this rocket, it would appear that the velocity of the air coming towards us was at 80 meters per second in the negative direction. So this is what this means. So we're assuming that if this direction is positive, that means velocity of the air with respect to the control surface is equal to 80 meters per second towards the left. So what about the velocity of the fluid at B with respect to the control surface? All right, so why is VA 0? VA, if we think back to our dynamics problems in relative velocities, VA is just the absolute velocity of the air with respect to a fixed reference. So if we're standing on the ground, there's no indication anywhere in the question about wind speed. So the air and the ground is just not moving. So if the air is not moving with respect to the ground, the absolute velocity of the air, which is the absolute velocity of the fluid at A that's entering, would be 0. Right, it's 0 with reference to a fixed coordinate. And then with reference to the rocket, so if we are now sitting on the rocket, the velocity of the air with respect to us now would be the same as the velocity of the air with respect to the control volume or the control surface. And that would appear to be minus 80 meters per second. So this is absolute. And this is also absolute. And this is relative. So if this is holding us up, review your notes from dynamics and relative velocity, because this will be important if we're doing problems with a moving control volume. And this shouldn't be the part that we're stuck up on too much. So that's for A. What about B? In the question, it says the velocity of the gas, the exhaust gas relative to the nozzle at B is 300 meters per second. So in this case, the question just gives us the velocity of the exhaust gas relative to the rocket, which is fixed to the nozzle, and that's just equal to 300 meters per second. And it's also towards the left. So we have our velocities at our inlet and our outlet with respect to our control volume. We can now go and write our continuity equation. So we know that the mass flow rate of our fuel in the question is given as 60 kilograms per second. And it's negative because it's entering our control volume. And we know the velocities of our gases, and so we know that the sign of those values too. So let's write our continuity equation. Partial derivative with respect to time of the integral over our control volume or density integrated over our volume plus the integral over our control surface times our density times our velocity of the fluid with respect to the control surface, dot product with dA is equal to 0. So if we have steady flow, that means that this quantity is just 0. And all we have left is the terms of our mass flow rates entering and exiting our control volume. So we have our velocity at our inlet at A, that is entering our control volume, so that's negative. So we have minus density of A times the velocity of A with respect to our control surface times the area at A. We have our exhaust gas, and that's exiting, so positive rho G, density of our exhaust gas times the velocity of B with respect to our control surface times the area of B. And then lastly, we just have our mass of our fuel flowing into our system, and it gives us that as a mass flow rate, and it's going into our system, so minus MF. So we have air, exhaust, and fuel. So we know the values for all these. So the density of air coming in set is 1.2 kilograms per meters cubed. Our velocity of A with respect to the control surface is 80 meters per second. We already have the negative out front because it's entering the control volume, and the area is 0.2 meters squared. We have the density of our exhaust gas. The velocity with respect to our control surface is 300. That's given in the problem. It's positive, so we already have the positive out front. And the area is 0.35 meters squared, which is given. And our mass flow rate above for the fuel is 60 kilograms per second. So if we rearrange this and solve, we get the density of the exhaust gas to be equal to 0.754 kilograms per meters cubed. Now I'll make a note here. So the trick in this problem was determining what was that velocity of our fluids at the inlet and outlet with respect to the velocity of our control surface. Let's do a third example where we have a deforming control volume. So in this example, we have a 1 meter diameter tank. It's filled with water using a 0.5 millimeter diameter pipe, which has a discharge of 0.15 meters per second. Determine the rate at which the level of water is rising in the tank. Neglect the effect of gravity on the falling water. So if this is water, we can assume this is an ideal fluid. So our density would be constant. So in this case, how the control volume is defined is we have a deforming control volume. So the boundary of this is the control surface, which is in red. And how it's deforming is at the instant shown, we have our lower rectangular section here, and we have our column of fluid adding to it. And this control volume is going to deform along these two surfaces here, and they're going to rise up to contain all of the fluid within this control volume. So let's go through how we would do that. So let's apply our continuity equation. So partial with respect to time, control volume, density times dV, plus integral of our control surface, density times our velocity, velocity of fluid with respect to control surface, dot product with our area is going to be equal to 0. So if the density is constant and the volume is only a function of time, then we can use total derivative. So the density is changing with respect to time and the volume is changing with respect to time. So for this term, we can rewrite it as rho dV dt. And then on the left-hand side, we only have fluid entering our control surface at the top right here. And since it is steady flow of an ideal fluid, we can write this as rho, it's entering, so it's minus rho times Q A. And since this is all equal to 0 and density is constant, we can divide both sides by our density. And the equation that we have is dV dt is equal to QA, which is equal to our velocity, 0.15 meters per second, times the diameter of the entrance pipe, which is 0.5 meters. So what can we do with this term on the left-hand side? What is an equation for our velocity? Or sorry, our volume. So this term here, we need to figure out some function for the volume. If we were just to sub in the volume change to the flow rate, we would just get the left side is equal to the right side. We wouldn't have any information about what the question is asking us, which is the rate at which the water level in the tank is rising. So let's write an equation for the volume where we use the variable y to describe part of the volume. So write in terms of y. If we do this, this will give us the most valuable equation that we can use to solve our problem. So if we look at this, we have the volume of the top section and the volume of the bottom section. We can use y and the diameters of each of those sections to help us figure out what the volume is. So for the volume of the top, we have 0.5 pi times 0.5 over 4 would be our area, and times the height would be 3 minus y. And the volume of the bottom section would be pi times 1 squared over 4 times our height y. So the total volume, the volume of the top plus the volume of the bottom, which would be equal to pi times 0.25 squared times 3 minus y plus pi times 0.5 squared times y. So this is our equation for V. We need to find the time derivative now, dv dt, the rate of change of our volume. We know y is changing with respect to time, so we should end up with a dy dt, which would give us the rate that our tank is filling up. That's the rate of change of the fluid height. So we'd end up with d dt of pi times 0.1875 y plus 0.1875, which is equal to 0.15. So this is our final equation to solve. We substitute this above. Let's say this is 1, 2. This is 2 into 1. So we solve this, and we end up with dy dt is equal to 0.8 over pi meters per second, or about 0.255 meters per second. So this kind of problem, there's multiple ways to solve it. If we wanted to solve it using control volume that's deforming as we've drawn above, and using our continuity equation, this is how we could do that. So we found an expression, a volume of our control volume is changing with respect to time, but our density is constant, so that can come out of this derivative over volume dv dt. It's equal to the net flow rates in and out. And then we found an equation for our volume with respect to the coordinates that are changing that we care about. We found the time derivative of that, and we set it equal to the right-hand side. And then we rearranged and figured out the time rate of elevation of the fluid as it's filling.